So our goal at the end of this lesson is to be able to solve exponential and logarithmic functions that are presented in different ways. So there's like 4 different setups that you might have, and so you have to be ready for any of the setups. The first way that we're going to solve exponential equations is to rewrite the equations by expressing each side as a power of the same base. This is very similar to how we evaluated functions in topic 2.4.2, So the first step is to rewrite the form so that the bases match. So this is when we're going to notice that the numbers are a part of the same power family. If we can get them to have the same base, then we can set the exponents equal to each other and solve. So for example, in letter A, I noticed that the base of 2 and the base of 16 can be written as a part of the same power family. So we could write this as 2 raised to the 3x minus 8 power being equal to 2 to the 4th power, because 2 to the 4th power is 16. So if I notice that those are a part of the same power family, boom, I have the bases written as the same, which means I can just make these exponents equal to each other. And now it's a cute little linear equation we can solve. Add 8 to both sides, divide by 3. We solve the equation, x is equal to 4. Make sense? The only way this can get harder is if the base that we're making the power family of is not necessarily shown. So what I mean by that is the base 27 and the base 9 are the part of the same power family, but it's not power family of 9s, nor is it power family of 27s. They're both a part of what power family though? 3. So if I rewrote this, I could write this as 3 squared raised to the x plus 3 power equal to 3, that's not squared, that should be cubed. Yep, And then 3 squared to the x minus 1 power. Now I've written this specifically like this on purpose, where the base 27, which is 3 cubed, and the base 9, 3 squared, are kind of contained in these parentheses. Because there's the property of exponents that we learned about last time or reviewed last time, where you have to take powers raised to the power and multiply them. So it's like there's a little distribution problem from the inside power to the outside power. So we actually have this written as 3 to the 3x plus 9 equal to 3 to the 2x minus 2. You have to distribute that power back to the other exponent. But once the bases match like they do here, we can just quickly set the exponents equal to each other and solve for x. Subtract 2x from both sides, subtract 9 from both sides. The answer here is negative 11. Okay, so that's the first kind of setup that you see. This is going to be, again, solving exponential equations when you notice the bases match or have the potential to match. But then we're going to have some problems where the bases cannot be written as a part of the same power family, in which case we're going to have to use the inverse operation of logarithms to solve these exponential expressions. So our first step is to isolate the exponential expression. That means we're isolating the thing with the power on each side of the equation. Once it's isolated, you're going to take either the common logarithm on both sides or the natural logarithm for both sides. 9 times out of 10, you're going to be using the natural logarithm because you only want to use the common logarithm when the base is 10. Otherwise, you're going to use natural log the entire time. Then you get to use the log loop or the properties of exponents to isolate the x and solve. So for example, if we notice this problem, 4 to the x equal to 15, 4 and 15 are not a part of the same power family, so we can't solve them like we did before. We first isolate the thing with the power. The thing with the power is 4 to the x, so we already are isolated. Check, done. We're going to take the natural log of both sides. This is the natural logarithm of 4 to the x equal to the natural logarithm of 15. So I'm just doing the natural log on both sides. What you do to one side, you have to do to the other. But your spidey senses should be going off. Based on the properties of logarithms we learned last class, what can you do with this floaty x? Move it to the front. Power to a power means multiply. So we're going to have x times the natural log of 4x equal to the natural log of 15. Oh, wow, what am I doing? No more x. It moved. Haha. We're one step away from isolating x. How do you get the x by itself? Divide by natural log of 4. So this is one of those problems where you're going to want to wait to the very, very end to type anything in your calculator so you don't round too early. Did I keep writing? Oh my gosh, what am I doing? Don't answer that. I don't want to know. Okay. So this is a calculator question. We're asking our calculator. With the fancy fraction, probably, it's usually nice to use that. That way your parentheses go in the right spot. Natural log of 15 divided by natural log of 4. And we're going to round, in general, to 4 decimal places in my class. Which means x is approximately equal to, when you type that in, 1.9534. Voila. Sound good? Here's another way that we might be able to solve a question like this. Again, 10 to the x power is what we're trying to isolate first because that's the term with the x in the exponent. So it is isolated. We're good to go. This time, since the base is 10, instead of using natural log, it's actually really helpful to use common logarithm. So doing log of 10 to the x equal to the log of 120,000. It wouldn't be wrong to use natural logs. You'd end up with the same answer. It's just actually faster this way. Because do you notice that we have log of 10? They cancel out. So what do I have left on this side? I just have x equal to the log of 120,000, which is something I can throw into a calculator. In your calculator, please type log of, this is a common logarithm, of 120,000. Should get 5.0792. Can I make it a little bit harder? Yeah, I'm going to do it anyways. Thank you for your honesty. Okay, what if I have this example 3? In example 3, the thing with the power is not isolated. So we actually have to do that first step of isolating the thing with the power. The thing with the power this time is e to the 0.06x. So if I was trying to isolate that first, what would I do on both sides? Plus 3 on both sides. So we have 40 times e to the 0.6x power equal to 240. And then I think you said the next step already. What is that? Divide by 40. Because again, we're still trying to get the e to the power isolated. So I'm dividing by 40 on both sides. We'd have e to the 0.6x. Very good. Yeah, so we're going to do the natural log, and we're lucky this time because we are using base e. It will cancel out that base of e. So we want to take the natural log of both sides. But you're right. These natural log and the e cancel each other out. This is 0.6x equal to the natural log of 60. One step left to solve for x. What is it? Divide by 0.6. So in my calculator, I'm doing natural log of 60 over 0.6, and we're going to round to 4 decimals. We should get approximately 2.9863. What did I do here? Oh, you're so right. Oh my gosh. I'm having a very Friday. Is that the right number now if you do natural log of 6? Oh, Lord. Okay, my bad. Okay, now that we fixed my typo. Let's look at the other example 3. LOL, they're both called example 3. My question for you is, the very first step in these problems says to isolate the base with the power. Technically, is this first base with the power isolated? Yeah. I know on the other side it's another base with the power, but as long as one or both are isolated, we can do this problem. So once it's isolated, we're going to take the natural log of both sides. I'm not using common logarithm, I'm going to use natural logarithm here. So we're doing natural log of 5 to the x minus 2 power equal to the natural log of 4 to the 2x plus 3 power. Now, the power properties of logarithms tells me that both of those exponents can go where? In the front. Now, when I put them in the front, because it's a binomial, I need to put them in parentheses, because this whole thing is being multiplied by natural log of 5, and this whole thing is being multiplied by natural log of 4. We're going to have some gnarly algebra happening here, because if you notice, natural log of 5 and natural log of 4, they're just numbers. Not yet. We're going to have to do this. And we're going to have to do that on both sides. So it becomes x times the natural log of 5 minus 2 times the natural log of 5 equal to 2x times the natural log of 4 plus 3 times the natural log of 4. Whoa, I just distributed a whole bunch of things. Yes. All of the x terms to the left side of the equation, which means I'm going to move this thing to the left. This becomes natural log of, what? X times the natural log of 5 minus 2x times the natural log of 4. I also want to move all of the terms without an x to the right-hand side. So I'm going to move this term to the right-hand side. So the 3 natural log of 4 is already there, and I'm going to add the 2 times the natural log of 5 to the other side. Pause and let's make sure we know where things went. Once we have all of the x terms on one side, I'm going to highlight this just to bring this to your attention. Do you see how both of those terms have an x in common? We can factor out x. Now this looks like we've done nothing to make this less complicated, but we're actually only one step away from being done. Because right now, there is a number, it's a complicated number, multiplied by x. And to isolate x's, we always divide by the number that's multiplied. So I'm going to divide both sides by all of this business. So that I end up with x equal to 3 natural log of 4 plus 2 natural log of 5, all divided by natural log of 5 minus 2 natural log of 4. That is all something that can be evaluated in a calculator. So grab your calculators, make it a fancy fraction, and you're typing all of that in at one time to get my value for x. And I'm going to pause and make sure everybody actually does this one.
Yeah, negative 6.3429.
Yeah, negative 6.3429. So this one's kind of gnarly, but only because the algebra gets kind of crazy. But we've technically done this process before when we did those square roots. It's the same idea of multiplying things out, moving all the x's to one side, factoring and dividing. It just looks gnarly because there are a bunch of natural logs in there. So don't lose what number is inside the natural log and what number is in front of the natural log. Another. Are you ready? This one looks rather complicated. Okay, can we isolate the thing with a power? Well, here's the problem. We have two separate things with powers. If you notice that there are two separate things with powers and they're different powers, this is actually a different kind of question. If you think back to chapter 1, this is in quadratic form. When we solved quadratic form equations or polynomials, we needed to substitute something into the equation so that we could factor it easier. So what we're going to do is we're going to let u be equal to e to the x. Why e to the x, you ask? Great question. I look at the middle term. Basically, whatever this is always squared of it. So we use this as u, which means I would rewrite the problem as u squared minus 4 times u plus 3 equal to 0. We factor. What are the things that multiply to 3 and add to negative 4? What are the things that multiply to 3? 3 and 1. If I make them both negative, don't I get negative 4?
Yeah.
Okay, great. So I have this right here. Awesome. If I substitute back in the e to the x, this is e to the x minus 3 multiplied by e to the x minus 1. Based on the zero product property, I can set either or both of those factors equal to 0 and solve. So I have the first factor, e to the x minus 3 equal to 0, and I have the second factor, e to the x minus 1 equal to 0. Using the steps we just learned for simpler looking exponential equations, we're going to add 3 to both sides. We're going to take the natural log of both sides. We're going to notice that natural log of e cancels out, yeah? We're left with x equal to natural log of 3, which we would throw into a calculator, and it's 1.0986. That's one of my solutions. We repeat all of those steps with different numbers. But it's parallel processes here. So we're going to add 1 to both sides. Natural log on both sides. Cancel out the natural log. We have x equal to natural log of 1. And we evaluate. Natural log of 1 is 0. Good, we remembered that property. There are my two solutions. It's a danger to look down in this class. And that is solving exponential equations. They can be real basic, like just this part. They can be real complicated if it's in quadratic form. And they can also be complicated if they're like the one above, where we have powers on both sides with different bases. Questions, comments, concerns for exponential functions? Because we're about to do logarithms. Yes?
How much time we can have it in the class?
At this rate, not a ton. Well, what's up? Oh yeah, we do have to move my tables for the PSAT. We're gonna make it work.
Can I try to go to the bathroom when you're moving the table?
Yeah. Okay. On the back here, we're gonna jump into solving logarithmic equations. And in my opinion, logarithms are a little bit easier to solve, except that they require a check step at the end. So in general, we're going to make sure we can write the logarithm in the form that it's usually looking like, log base b of something equal to some number. And you're going to use the log loop to solve it. So we're going to want to make sure we remember that loop, which I think that we did, so that we can loop these around to create an exponential. 9 times out of 10, doing that loop allows you to solve then a linear style function to get your answer. For example, and actually, let me make sure that I've highlighted this. This is our isolate step, because there are going to be times when you have to isolate the logarithm. In this first problem of number 5, the logarithm itself is already isolated. You see how log is by itself, which means we're ready to just do the loop. What's the base of this logarithm? 4. If I were to loop it, this would become 4 to what power? We loop it. 4 to the second power equal to x plus 3. Oh my gosh, guess what? This is super easy now. What's 4 to the second power? 16. If 16 is equal to x plus 3, what is x? 13. Awesome. But here's the thing. We can't just stop after getting an answer. We do, when we are working with logarithms, always have to check our work. Okay, this is not an optional step because checking your work will allow you to make sure you don't have an extraneous solutions. Logarithms have restrictions on their domains, so we have to make sure we can actually plug that number in. All we have to do, though, is take the number we got and plug it into the inside part of the logarithm, this x plus 3. If I plug in what we got, which was 13, 13 plus 3, what is 13 plus 3 equal to? Is 16 greater than 0? Then we're good. If ever you do that step and the number you get is less than 0 or equal to 0, you have to throw that answer away. It can't be used. That would be an extraneous solution. So the check step is a part of the solving process here. Let's do another one. Let's say I have 3 times the natural log of 2x equal to 12. Right now, is the logarithm isolated? No. So what do we do to get that 3 to go away? Divide by 3. So I have natural log of 2x equal to 4. At this point, now my natural logarithm is the only thing on its side of the equation. Yes. Yes. We go for the loop. What's the base here? E. This is going to loop to be e to the 4th power equal to what? 2x. If I'm isolating the x here, what do I divide both sides by? 2. So x is going to be equal to e to the 4th power divided by 2. That's going to be something we can throw into our calculator. Do y'all remember where the e button is? Okay, in your calculator, do e to the 4th power and then divide it by 2. We should get approximately 27.2991. Is that what y'all got? Fabulous. However, we have to check it. We are checking this by plugging it into just the inside part. Again, just the inside is what we're checking. So we do 2 times 27.2991, which is going to be 54.5982. Is that greater than 0? Yeah, so we're good. There will be times when the answer you get is not, so we always have to check our work just in case. Two more. Now this one. We're still solving this logarithm, but what do you notice is different in this problem that was not in the other 2 problems? I heard somebody whisper it. There's 2 logarithms. So we think back to what we did last class, and we have to condense it down to 1 so that we can use our skills. But I see here from last class we have an adding sign. What does that mean I'm doing with the stuff inside the logarithms? Multiplying. So this becomes log base 2 of x times x plus 7 equal to 3. Once the logarithm is isolated, which it is, there's only one logarithm on that side, we're going to loop. What's the base? 2. What's the new power? 3. And that's going to be equal to x times x plus 7. I can't help myself. Let's just go ahead and distribute this. This is x squared plus 7x. What is 2 cubed? Don't say 6. 8. So we have 8 equal to x squared plus 7x. My brain is going off and saying, oh, wait, this is a quadratic. When we solved quadratics, we set the quadratic equal to 0, and then we factored. What numbers multiply to negative 8 and add to 7? Plus 7 and negative 1. The zero product property here tells me that I can set each of these equal to 0. Oops, I was getting ahead of myself. And solve, which means x is equal to -7 and x is equal to 1. Awesome. Except one of these is not going to work. Wait, 7? Guys, y'all like letting me do these crazy things? What am I doing? That's 8, right?
Yeah. I think that was my fault.
Isn't it -7 and -1?
No, because it's multiplying to 8, adding to 7. That was my bad. I confused us. Okay. Now, because we have two solutions here, we definitely want to check, because most likely there's only supposed to be one. If we start plugging these questions into either of the arguments that we started with, both this argument or this argument, one of them will not work. Obviously, right away, which one will not work? The -8 is not going to work, because -8 is not bigger than 0. So we have to throw it away. But if we check the other one, is 1 bigger than 0? Yes. And is 1 plus 7 bigger than 0? Yes. So we got the yeses for both insides of the logarithms from 1, which means we only have one solution, and it's 1. We have to check all of the arguments. Now we flip the page. There's one more way a situation can be presented to you for logarithms, and that's if you have logarithms on both sides. So we're going to add that little title here because I don't think it says that on here. This is logs on both sides. If you have logarithms on both sides and they both are the same base, then just like when the bases matched in an exponential, if the bases match in a logarithm, you can set the stuff equal to each other and solve. So I notice in this problem that we have here, we have logs on both sides. We're going to make sure we can first condense the logarithm down so that it is in the form where there is a log on both sides. Why won't this change to the color I want? A log on both sides with the same base. That means we're probably condensing things down. Then we use that one-to-one property to set the insides equal to each other, solve, and check our answer. So if we're doing this one, here's what it would look like. I see that there is a minus sign right here. Based on what we did, bye, have a good weekend. Based on what we did last time, what do we do when we subtract separate logarithms? Divide them. So this is going to be natural log of x plus 2 divided by 4x plus 3 equal to the natural log of 1 over x. Once logarithms are equal to each other and they have the same base, these are both base e, we basically can ignore the logarithm. We can just set the insides equal to each other. If those logarithms are equal, then their arguments are equal. Do not panic about solving this one. I'm hoping your brain started to want to kind of do this number. This is a classic move. Oh, it's not changing the color I want. What is this? Butterfly method, cross multiplying and dividing. We can do that. 1 times 4x plus 3 is 4x plus 3. And x times x plus 2 is x squared plus 2x. What kind of equation did we just create here that we need to solve? A quadratic. No problem. We know how to do that. We're subtracting 4 from both sides and subtracting 3 from both sides, setting the equation equal to 0. We're factoring like we've done since forever. What are the numbers that multiply to -3 and add to -2? -3 and +1. We're solving both of those using the zero product property, x equal to 3 and x equal to -1. But then we're going to check our work because most likely one of these things is going to go away. Now, the easy part here is that we're not checking our work with the complicated work that we did. We are checking these numbers in the original 3 arguments. Looking at the original 3 arguments, Let's check the number 3 first. Is 3 plus 2 bigger than 0? Yeah. For the next one, it's 4 times 3 plus 3. That's 12 plus 3, which is 15. Is that bigger than 0? Yeah. And if I do 1 over 3, is that bigger than 0? 3 check marks. We're good. We checked all 3 arguments. When I check the next one, this is going to be negative 1 plus 2, which is 1. That's fine. 4 times negative 1 plus 3. Well, 4 times negative 1 is negative 4. Plus 3 is negative 1. Is that one bigger than 0? No. So right away, once I get a no, I'm going to go ahead and throw that one away. That's an extraneous solution. We just have x equal to 3 as a solution to our logarithm. So we have to combine the skills we had last class of condensing logarithms to be able to solve them. And when you solve, you might end up solving a linear function, or you might end up solving some sort of quadratic. So you got to keep using all of those skills from previous chapters as we add more complications to it. Huh? That's it? You can go to the bathroom, yeah.